Hey guys, today we are going to be graphing polynomials and kind of talking about a polynomial and its behavior. And we're going to do this without using a calculator. So you've been used to throwing these types of equations into your calculator and talking about minimums and maximums and stuff like that. And now we're going to learn how to graph things that may not be an easy line or a quadratic using certain traits of polynomials. So your essential question is, how do I graph a polynomial without using a calculator? And let's start. Again, we are on the note skeleton, and we're going to begin with We're going to begin by talking about end behavior. So the end behavior of a graph is just talking about what is the graph doing as x is going either to positive infinity or negative infinity. And so you might remember hearing this as horizontal asymptotes when we're talking about kind of, what is the graph doing at the end? Is it going up? Is it going to be going down as it goes a certain way? That's all we're talking about. And so there's a kind of a little chart right here for us to look at, to think about when we, different degrees and different leading coefficients of your polynomial in order to determine the end behavior. So the first thing that we look at is, remember, we look at the degree of the polynomial. So we want to find the highest exponent in there. And so if that degree is odd, it's going to follow this first row. And if it's even, so it's 2, 4, 6, 8, it'll be over here. The other thing we're looking at is the leading coefficient. If it's a positive leading coefficient, you'll be using this column, and negative, you'll be using this column. So let's kind of talk about an example here. The first thing is that if we had an odd degree polynomial with a positive leading coefficient, the easiest one I can think of, an odd degree, would be 1. And if it's a positive leading coefficient, I would think of y equals x, the linear parent function. And so when you think about this graph, that's just that line with a slope of 1 goes to the origin, and you notice here that your graph is going down this direction and going up that direction. Okay? And so that's what anything that has an odd degree with positive leading coefficient is going to do. So if you look at this guy, in the end it's going to be going up. In the beginning it was going down. And it can do a lot of weird stuff in the middle. It could have lots of x-intercepts, it could have a bunch of loops in it, but this would be an example of a polynomial that has an odd degree with a positive leading coefficient, because it's going to have these kind of arrows going on. So we're kind of looking at the blue here. So with this notation, this is going to be stuff we see a lot in the future. As x approaches, that's what this little arrow means. As x is going to infinity, y, positive infinity, y is also going up. So it's also going to infinity. Okay, so if you want to write a little up. Okay, same deal here. As x goes to negative infinity, that's going to the left, y is going down, so it's going to negative infinity. Okay, and so again, if you have an odd degree with a positive leading coefficient, you're going to have that down-up thing going on. So it's going to look like that. Okay, now negative leading coefficient with an odd degree, we're going to think of another one that we use a lot, and that's y equals negative x. Okay, and so if we think about that guy, again, this has got a degree of 1, and with it negative, all it does is it flip-flops the slope. And so when you look there, you see that it's going up and then down. And that's what this polynomial is going to look like. And so if we had my arrows, that's how it's going to end. And who cares about what it looks like in the middle right now? We're just dealing with the end behavior. Okay, and then when I look at this little, whatever you want to call it, sentence down here, as x approaches infinity, now as x gets bigger and bigger, y is going to approach negative infinity. It's going down. And as x approaches negative infinity, y is going to be going up. Okay, and so you're going to have this behavior going on. All right, now let's look at those even degrees. Even degree, 2, 4, 6, 8, all of those. And so we know one of our favorite even degree polynomials would be y equals x squared, that quadratic parent function. And if I think about what the graph looks like of that guy, it's that u that has both of the arrows pointing up. And so that's what this type of polynomial looks like. Up and up. So it doesn't matter what it looks like in the middle. Could be a regular u, could be some weird squirrely thing, and that's probably not even a function, but it's going to be going up and up. So as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y also goes to infinity. Okay, so we have that up and up. Okay, last but not least, same deal here. If we have a negative leading coefficient with an even degree, that could be like y equals negative x squared. And if you remember with a quadratic, all that does is make your u face downward. So you're going to have both of your ends going down. So down, down, and again, you might have something nice on the inside. You probably don't. Whoop, that is interesting. And then as x goes to infinity, y goes to negative infinity, down, and y would also go to negative infinity on the left side. Okay, so down, down. So that's kind of, it gives you an idea of what the ends of the graphs look like, so then you can just worry about the middle using the rest of this stuff. Okay, so that is the general idea of end behavior. The second thing that you're going to look at when you graph a polynomial is your intercepts. And so the first intercept is going to be your y-intercept. And what you're going to do here is you're going to plug in 0 for x. Okay, that's just finding a y-intercept. And y-intercepts are easiest to find when your equation is not factored. So if you're given an equation that's not factored, let me finish my thought, then you can usually figure this out and then factor it afterwards, just to make sure that it's easier for you. So for instance, if I had this guy, I wanted to find the y-intercept. If I put a 0 everywhere there's an x, that would cancel anything out besides this last term. So I know that my y-intercept of this guy would just be 0, -7. It's not impossible to find the y-intercept in factored form, it just takes a little bit more effort, and it's kind of not fun. Okay, the next thing we're going to look for are our x-intercepts. And x-intercepts have a lot of names, if you remember, especially back in quadratics. We call these roots, we call these solutions, we call them x-intercepts, and the one that we're going to use a lot is zeros. Okay, so we're looking for the zeros of a function, we're looking for where it's crossing the x-axis. So in order to find these, and we kind of talked about this with quadratics back in the day, the polynomial really needs to be in factored form. Because then what we can do is we can just set each factor equal to 0 and solve for x, and those are your x-intercepts. So y-intercepts, we'd prefer it to not be in factored form, but to find the zeros, we do need it to be in factored form. So here's an example. This guy's already factored for me, really nice, and we just take each part of it and we set it equal to 0. So this guy is a factor, so we'd set x equal to 0. We'd set x minus 3 equal to 0, x minus 2 equal to 0, and x plus 7 equal to 0. And if you notice, I know that this 3 means that there's 3 of those, but if I set that equal to 0, it's going to give me the same answer any time. So we don't have to set, do this 12 times. We just have to do it however many factors it has. And so then you just solve them for x. So that guy's already solved. So if you wanted to go off to the side and be like, these are all my zeros. One of my zeros is 0. One of my 0 is going to be, if I add 3 to both sides, so I'd have 3. This guy's going to get me positive 2 if I add 2 to both sides, and this guy is going to get me negative 7. And so those are all the zeros of that polynomial. Okay? And last but not least, what we need to think about when we are graphing a polynomial is called the multiplicity. That's a new word, and it's kind of weird, but all it means is what is the graph doing at that intercept. So in order to figure that out, that's where we're going to care about if it's a cube, if the factor was to the 7th power. This is where that comes into play. So the multiplicity is going to tell me what is it doing at each of these intercepts. And there's 3 different things it could do. The first thing it might do, if you have a multiplicity of 1. So if you have, for instance, a factor that's like x plus 3, or you had just an x, or x minus 2, or whatever. This is just a degree of 1. Okay, so to the 1st power. And what's going to happen at that point, at that x-intercept, is your graph is going to cross the x-axis. If you think about the graph of y equals x plus 3, it's just crossing at that 0. Okay, it could cross going negatively, but again, if you have a multiplicity of 1, if it's just a regular linear factor, it's just going to cross right there. Now, if you have a multiplicity of 2, what that means, or sorry, even, so 2, 4, whatever. So if you had something like x squared, that would have a multiplicity of 2. Maybe x minus 2 to the 4th power. And so if you think about when we had x squared, you know, x minus 2 squared, any of those type of ones, what's going to happen at that root, or that 0, is the graph is just going to touch and then it's going to bounce back. You might see this listed as the word tangent, which just means it touches once and then it goes away. So like for instance, if you had a 0 right here, all that's going to happen is your graph is going to touch that 0 and then bounce away. Or it could come from the bottom and touch that 0 and bounce away. Okay? And so it kind of looks like that quadratic. It's bouncing off the 0. The last type of multiplicity you could have would be odd, and it's odd that's not 1, because obviously if it's 1, it's crossing. So if it's odd, you had, you know, x minus 4, it's like the 5th power, x cubed, and what that does is it's called a wiggle. We're going to be super technical here. We're going to have a wiggle. So if you think about that parent function y equals x cubed, that's what happens at those roots, because you remember back in the day, this one has that root there, and it does this weird thing where it kind of squishes in the middle, and that's what that wiggle does. So if you had a 0 right here, you would have this type of shape going on, or maybe it was decreasing at that spot and it would do that little wiggle, and that's an important feature of the graph, so we have to make sure we kind of show it. Okay, so what we're going to do is take all of those 4 things and we're going to practice graphing a polynomial. So here's my example. So one we used when we found the zeros. And we want to take this and we're just going to sketch a graph. It's not going to be pretty. Okay, it's going to be an idea of what the graph would look like. So we're going to start step 1 to find out what the end behavior is going to do. And in order to find your end behavior, remember, this guy is in factored form. So you are looking for your highest degree, and in order to find your highest degree, you need to add all the exponents together. Okay, because if I multiplied all these things out and did everything, if I add all the exponents together, that would be the exponent of my degree. Okay, now if it's not factored, you just look for the biggest exponent. So since this guy's factored, it's pretty straightforward. This guy has a degree of 1, or an exponent of 1, so I have 1 plus 3 is 4, plus 4 is 8, plus 1 is 9. So I have degree 9, which means that I have an odd degree. And then I look and I see that the numbers in front of all of my x's, so the one in front of my highest exponent is just going to be 1. And so that's a positive 1, so it's a positive leading coefficient, which means if I look back at my chart, I'm going to have the same end behavior as the graph of y equals x, so it's going to be going down and then up. And you can just kind of sketch that on your graph to start with. You know that this is going to be the end. Okay, now we're going to find the y-intercept, and remember, we find the y-intercept by plugging in x equals to 0. And this is in factored form, so you're going to see it's a little bit more tricky to figure it out, because wherever you have an x, you have to plug in a 0. So if I had negative 3 cubed and negative 2 to the 4th and times 7, it gets kind of big. But the nice thing is that if you put a 0 in here and you multiply it out, everything's going to cancel. So my y-intercept is actually going to be at 0, 0 for this particular example. And then we found the x-intercept before in the other part, where is it? A number 3 in part 3. So I'm going to list those out again. I'm going to do a different color. And so we found that those zeros were 0, positive 3, positive 2, and negative 7. And when you're finding those x-intercepts, remember, it's not just important to find out where they are, it's also important to figure out what the multiplicity of that factor is, and then what the behavior is going to be there. So the multiplicity of this first one is just 1. It's the exponent on that term. And if it's just 1, what that means is that it's going to cross at that point. Okay, and we saw that it's going to cross that axis. Then we're going to have x. Okay, and then 3, if I look at that factor, I can't even see it, this has a degree of 3, so the multiplicity is 3. That means that it's odd, but not 1, so it's going to wiggle there. Okay, and then same deal, that one has a multiplicity of 4. That's even, so it's going to have that touch or that tangent. And finally, -7, that has the multiplicity of 1, which means that it is also going to cross right there. Okay, so I'm going to plot those. Again, it doesn't have to be perfect. I'm just going to kind of get an idea. Here's -7, there's 0, here's 2, here's 3. And then I'm going to draw those things in. So at -7, I'm going to erase this and kind of move it over. Can't see anything. At -7, it's going to cross. So we're just going to draw my graph and cross right there. Then the next 0 is at 0. So I need to go and get back to that 0, go through it and cross through it. Then at 2, it's going to touch. So it's going to do this weird thing where it's going to go up and come back down. And then finally at 3, it's going to wiggle. And this is the hard one to draw. You go in and you kind of make sure it looks weird. It's still crossing, but it has that weird little flat part in the middle. So if you notice, this is not drawn to scale. I don't know what my maximum y values are, so I didn't even label my y-axis, and this is just a rough sketch. Doesn't have to be perfect, you just get the idea. Make sure you label your zeros out and make sure I can tell very clearly what the end behavior looks like. Okay, this next example I'm going to do is going to be optional because I know that this video is running a little bit long. So if you want to keep watching, great, and you can do this last example with me. Otherwise, I will see you tomorrow. Okay, so here is this optional example. So this is my function that I'm going to be graphing. And this is a little bit set up a little bit differently, but you still need to find all of those pieces of information. So this one kind of walks me through the end behavior piece where you're looking for what's my highest powered term so I can decide what the degree is and what the leading coefficient is. So if I look at my highest powered term, if I had multiplied every single thing out, you notice there's a 1, a 1, a 1, so there's going to be 2 times 1 is 2. And then I go ahead, and since this is in factored form, I can just add up all of the exponents. And so that's 2 plus 1 plus 1 is 4. So that would be my highest powered term, which would then mean that I have a 4th degree polynomial, so that's even, and it has a positive leading coefficient. Okay, and so if I look, if it's even, has positive leading coefficient, it's going to look like x squared where it goes up and up. Then I want to go ahead and find my y-intercept. So if I go ahead and wherever I see an x, I'm going to plug in a 0. So I'd have 0 plus 1 squared, and then I'd have 0 minus 3, and then I'd have 0 plus 5. So here you can kind of see where it's going to get a little bit messy. So I'd have 2 times 1 squared is just 1 times -3 times 5. Whenever you get into those crazy higher powers, it's going to be even worse. And so that means that my y-intercept is going to be at 0, -30. Now you may not have to plot this on the graph exactly where it needs to go, but you kind of have an idea that it'll be underneath the x-axis where that y-intercept is. Okay, then we go ahead and we find my zeros. And so my zeros are, again, you set each factor equal to 0. So in order to make this guy 0, I'd need a -1. This guy would need to be a +3. This guy would need to be a -5. And then I look at the multiplicity of each of those zeros. So this x plus 1 factor was even, and so evens are going to touch. Okay, and then the rest of them were just 1, and so that means it's going to cross and cross. I'm going to go ahead and plot those zeros on my graph. So I had -5, -1, and 3. And then I remembered that it's going to go up and up at the ends. So at -5 is going to cross, so I'm going to let my graph go through. At -1, it's going to touch, so it's going to get close to that -1 and then bounce off. And then at 3, it's going to cross again, so it needs to go past the y-axis. Wow, I just messed that up. And then cross through that 0, and then there's your graph. Okay, I will see you tomorrow. I hope that helped clear up anything, and we will continue sketching polynomials.